The objective of the project I will describe in this video is to determine if solar energy can be used to make distilled water. The project is being funded by the state of Florida and is being operated in conjunction with the Mote Marine Lab, who has provided the site behind me for this purpose. The technology being investigated is owned by Solar Ventures Limited, whose managing partner is Ventures Plus Incorporated, and the technology is patented. The whole idea here is to see if we can take solar energy and convert hard water or salty water into drinkable water. What you see behind me are solar collectors on wooden stands. The collectors measure 4 foot by 8 foot and are therefore full size and are of an industrial type. The importance here is that solar energy does not cost anything. The sun shines and it's free to us. Our job is to determine if we can take this free sun energy and make high enough temperatures in these devices to make steam. If we do that, we can later separate the steam and condense it to make very pure distilled water. And that's what we're up to with this technology. In fact, we have done that. And what I want to do now is take you through and show you the system and the individual components and tell you how we have gone about making distilled water using this technology. These collectors are conventional in the sense that in this box, it really is a big box, in the bottom is an absorber, which is a piece of copper metal painted black. The blackness of the metal is the thing that it absorbs the sunlight and converts it into heat. Underneath the absorber, black metal, are copper tubes through which the water runs and is heated from the absorber. The absorber is at about this level, and there is simply a box around it and some thermal insulation underneath it and in the sidewalls. Conventionally, this collector would lose a lot of heat through the top. The same place the sun comes in, the heat will go out. The invention here, and this is patented technology by Solar Ventures Limited, is that we keep the heat from going out. We allow the heat to go in, but we allow the sunlight to go in, but we keep the heat from going out. So we call this thing a transparent insulator. It is an insulator in the sense that it provides a thermal resistance, as does fiberglass. In fact, the thermal resistance of this unit is twice as good as fiberglass. But it also allows the sunlight to come in almost totally unimpeded, and it works very well. Conventionally, collectors of this nature would only attain temperatures of about 150 to 180, whereas in these systems we've gotten temperatures up to about 265. As you know, water boils at 212, so we are making steam in these collectors, which is precisely what we want to do. We then take the effluent from the collectors, the water stream from the collectors, put that into a vessel that you'll see in a minute or two called a flash tank, whereupon we separate the hot water from the steam. The steam comes issuing out at the top, the hot water is sent back to the collector system, and once the steam comes out of the top, it is condensed to make distilled water. The characteristics of this transparent insulator are unique and, as I said, patented. Basically what we do is we provide a baffle here to prevent convection from going around in the box. Once the absorber gets very hot, the absorber, by the way, will get up close to 400 degrees Fahrenheit. Once it gets hot, it generates a lot of thermal currents, which will transfer the heat from the absorber to the top glass where it is lost. The circles you see on the top of this transparent insulator, in fact, are a set of baffles that prevent that from happening. The system also prevents re-radiation of the light, loss of the heat from infrared radiation to the dark sky or to, in fact, the blue sky. So the thing operates on a mode of preventing convection and re-radiation, and therefore allows these collectors to get almost 100 degrees hotter than a collector without this transparent insulator. That is 100 degrees F. However, that's the collector design. The project focus here is to make distilled water, and we'd like to take you to the next step to show you, in fact, how we separate the distilled water, how we separate the steam from the hot water and make distilled water, and that will be the next sequence. Before we go and show you the separator which separates the steam from the hot water, I thought perhaps we ought to take a look at the entire system. We talked about the collector with the transparent insulator. Let's talk about the rest of the system. The water we use in this project is stored in tanks like the one you see right here. Each system has its own separate tank. This one happens to be 50 gallons in capacity, and we put about 40 gallons of water in it. What happens is that the water from this tank is circulated through all these collectors, or this collector system, around and around until we're ready to do something with it. It is circulated through this system by this little pump you see on the ground right here. It's important for us to know how much water we are passing through these collectors at any one point in time. So what we do is we measure that flow in gallons per minute with a flow meter designed for that purpose. The flow meter is here, and if you can see, there is a round metal bob in there which tells us at this moment that we are passing water through these collectors at 2 gallons per minute, or roughly 16 pounds of water per minute. Now the only other element in this whole system is a timer that we have on the ground, and the purpose of the timer is to turn this plant on in the morning automatically and shut it off at night automatically, so that the labor component is reduced because we have automatic turn on and shut off. But the whole operation is turned on and off automatically. It requires virtually no attention at all. It operates pretty much on its own. Now let's take a look at the separator, which in fact will separate the steam from the hot water, and we'll go around this way. When we're ready, when the temperature gets hot enough in the collectors, currently it's about 257 degrees Fahrenheit, we decide that we want to separate the water from the steam. What we do is we open a valve back here, and the water from the collector comes through this line into this flash tank or steam water separator. Although it's not apparent, this is the inlet, and there is a pipe inside which traverses to the side of the tank, whereupon, by the way, at 257 degrees, we probably have 30 pounds per square inch pressure inside the collectors. So when we open the valve, and this is at atmospheric pressure, when we open the valve, the hot water steam combination comes surging through here, exploding in our flash tank, and the hot water circles around and goes to the bottom of the tank. The steam comes out of this big pipe here, goes over to our heat exchanger where it is condensed and collected. So let's watch this again. The mixture of steam and hot water come through this line here into the top of the tank. It is exhausted to the side of the tank. The hot water goes spiraling down. The steam comes shooting out of this larger pipe, comes through here. Cold water goes through on one side. The steam comes in outside the tube and is condensed by the cold water. We collect the condensed steam as distilled water. We have a sight glass in here to tell us how well we're operating, because, or where we're operating, because you may be able to see a pump behind here. We do return the hot water to the system. We will do this several times a day, and we are beginning to consider doing it on a constant basis. So there's a constant flow of hot water and steam into this device, constant flow of steam out, and a constant return of hot water to the system. And this is a very critical part of our operation. It is the separator. and otherwise this whole system is very simple. In a few minutes we expect to show you the venting of the hot water steam into this tank, and we're going to put a temporary surge bottle here so that you can see the steam issue from it, because we think that's a very dramatic circumstance. Oftentimes it has made people jump back when the steam goes roaring through here. So we would like you to see that. But before we do, let me call your attention to the trailer behind us. This is in fact where we collect our data. The temperatures are monitored at all times from early morning to late night for this entire collector system. This is, by the way, if you can show up here, Mr. Cameraman or Mrs. Cameraman, we have these covered, but in fact, can you see this? This is a thermocouple. It's an electrical device that sticks into the water stream and measures the temperature and is transmitted according to these thermocouple leads back underground into the trailer where the data is recorded on a data logger system in there. So we have a constant supply of information regarding what the temperature is in and out of each one of the collectors that we are employing at all times. As I mentioned earlier, we do record the data, the temperature data, on a data logger or system that's provided for that. And here it is. This is a data log in the multiplexer. Currently the temperatures are, as we'll show in a few minutes, they're quite high. One system is around 240, the other system is around 250 or higher. In fact, maybe we can actually physically show this data as it flicks on and off. These are the temperatures in degrees Fahrenheit. One system is, that's the ambient temperature there. It's 87 degrees outside today. There's 254, 254, 255, 257 for a second there, 256, and now the other system is 234, 237, 235, 237, 237, and the ambient is now 88 degrees. Can you see that? Okay, fine. So you can see the kind of temperatures that we are attaining today. This is considered a reasonably good day in Sarasota, Florida in the summer. In order for us to determine how well we are operating, we need another piece of data, and that is the amount of sunshine we get on a daily basis. And for that purpose, we have pyranometers located on that pole that record the sun intensity on a strip chart minute by minute, so we can compare one day with the next. As I told you earlier, this is our flash tank. In this case, instead of having the steam go into our condenser unit, we decided to have it travel into a 5-gallon glass jug, which has been cooled, and you will see the steam come out of the jug itself. We want you to see that. That's why we put this temporary system in here. Normally we don't do it this way, but we wanted you to see the steam. The temperature currently is around 254 degrees. We're going to open this up and see what happens. You also should listen as well as look, because this flash separator will start making all kinds of noise as the water boils, and it violently boils in this separator with the steam issuing out. So you should listen as well as look and watch it jiggle around. It should do that. Go ahead, Kirk. He's opening a valve now to let the... can you hear it? You can see the steam issuing out of here, and you can hear the boiling in the tank. Can you see the tank jump around? It's because it is boiling in there. Steam is coming out in great abundance. If we didn't have this there would be considerably more volume for you to see, but it would be more dangerous. But you can see the tank jumping around, no question about it, because the water is violently boiling in that tank. We'll do this for an extended period of time. We will not take time to allow it to go to the end. But this steam then is condensed in this unit here to make the still water. You notice you can already see condensation on this tank here. That is the still water. You can see the condensation going. This is a very inefficient way to do this. I'm not suggesting this is the way it should be done, but this is simply to demonstrate what transpires. Notice the surging and purging of the tank here. The energy involved in this operation is incredible. All of this comes from sunlight, folks. This is all made with free sun energy. In any event, at this moment we can tell you, even though the project has not been concluded, we can tell you that we in fact can make distilled water from whatever we start out with, using this system here and free energy from the sun and the solar collectors. I might mention to you that the water is now coming up in a sight glass, so we vented probably in the neighborhood of 15 gallons of hot water there, which normally we would return to the system. We are not doing that now because this is simply a demonstration. But normally we'd return that hot water to the collector, and I'm going to have to conclude because I'm getting very warm here. Let go, Kirk. We discovered that we didn't have the valve wide open, so you can see the real volume of steam coming out of here. We have now opened the valve full tilt, and you can see the steam coming out. I'm sorry that we didn't realize it, but the valve was not fully open, and as a consequence, the discharge was not as full as it could be. But you can see now what's actually transpiring here. A good bit of steam is coming out of here, and the condensation in the bottle is even heavier than before. And this will go on for the next 15 minutes, 30 minutes, or even longer. Is that valve open all the way now, Kirk? See how violently the steam, you can see how violently the steam is issuing from here. Okay. We now have emptied the storage tank to the extent of about 1/3. There's still a considerable volume of water and steam in this system. Probably another 2 times as much as you've seen so far. What? So we need to shut it off? Okay, we're going to shut this down now because I think you've seen sufficiently what can be done with this technology. And again, thank you for your time and attention. I'm sorry we didn't have the valve open all the way the first time. The first part of this video was made in July of 1991. It is now March of 1992. And we're about ready to complete this project. And in view of that, I thought you might like to know what transpired since July and in fact throughout the project. So this part of the video is going to be directed at what we consider our accomplishments throughout this project. Within a couple of weeks, this equipment behind me will be dismantled and moved somewhere else. And so this is an opportunity for us to tell you what was accomplished throughout the project. But before I do, I want to call your attention to the fact that we have considerably more equipment in this plant now than we had before. In the early part of the video, we had 5 collectors operating as a plant, a fully integrated plant. We now have 12 collectors operating in the same mode. They're turned on as before automatically in the morning, and they're turned off at night automatically. So it's the same kind of thing except more collectors. We've expanded the plant quite considerably since July. Now let's talk about the accomplishments. Also, by the way, I should mention we have different kinds of collectors. You can see some on the ground here and others on the stands. And they're obviously different kinds of collectors. They were used for different purposes. As far as the accomplishments are concerned, when we came out here, we wanted to determine if we could use only sun energy, solar energy, as the primary energy source to make distilled water or drinkable water from either hard water or salty water. In fact, we have done that. We have made significant quantities of very pure distilled water using this equipment in a process that you have just seen in the previous part of the video. When I say very pure, the analyses were conducted by our partners, the Mote Marine Lab, and we found that at times we made water with about 4 to 6 milligrams per liter of total dissolved solids, which is as pure as any distilled water you can buy in a grocery store. In fact, probably a little bit more pure from the point of view of total dissolved solids than much of it. It also is, by the way, considerably more pure from the point of view of total dissolved solids than your tap water, for example. Besides that, we made some other accomplishments. For example, the Mote Marine Lab took some wastewater bacteria. They put them in our tanks in the morning and infected our water supply with bacteria, and we took samples every hour on the hour. By midday, we had reached a temperature of 215, and we killed all the bacteria. So in fact, not only do we make very pure water, we also make sterile water. You might wonder why that's important, and I would respond to that by saying that this technology may one day find application in remote places, third world countries that have hospitals and laboratories way out in the hinterland, and making not only pure water but sterile water for their purposes would be quite essential. And there's some value to that. And in fact, maybe even in the United States, but most especially in third world countries. We also did some other things. We tried to take a look at the economics of this process. We haven't finished that. I would suggest that we have. But the initial indication is that we can be competitive with any process making pure water today, drinkable water, either reverse osmosis or reverse dialysis. As I said, we're not finished with that study, but there's a lot of indication that we can be very competitive. Doing all of this would be great, but if it costs 10 times more than it costs currently to make water by other means, we would not have contributed much. It appears that that is not the case. Now, there's no question about the fact that in the early part of the video, you saw the huge amount of steam coming out of this collector system, which we vented in the air just to show you how much steam there is in it. I'm sure it has occurred to you that we can do things with that steam other than to condense it to make distilled water. In fact, we think we can. For example, we may be able to use that steam to make mechanical energy by sending it through a small turbine or gas-driven pump, and thereby make mechanical energy which can be used in a variety of tasks. For example, it could be used to pump water through agricultural fields in remote locations again, or to bring water from nearby aquifers to the ground and distribute it through agricultural fields in places like the Middle East. Another potential application for this technology is to couple it with that already existing for solar air conditioning, and thereby air condition various places with this combination of technology. This technology would provide the heat source to drive water off the desiccants in a desiccant air conditioning system, or be coupled with an absorption system in a conventional way to make solar air conditioning. We think there's a good chance to do that, and we would like to pursue that. Another potential application has to do with environmental materials, environmentally unacceptable materials. For example, this technology can be used to boil off the safe solvent in a mixture of environmentally bad material and a solvent to consolidate it, so you only have to discard much smaller quantities of the bad material than you would otherwise. There are other potential applications in the environmental field for this technology. One of them is to steam distill solvents, organic solvents, out of mixtures like dry cleaning emulsions to recover the solvent and then have to throw away much less environmentally unacceptable material. So there are a large variety of potential applications for this technology that we have not explored yet. The basic technology has been developed. This application for distillation has gotten this far. We need to go a bit further to make it economically feasible and proven, and to bring it into the commercial marketplace. We think we can do that. We think we can also develop applications for the technology in the other areas that I've mentioned. We hope to be able to do that in the future, and if we do, we hope to be able to bring you this story with other applications. We very much appreciate your taking the time to look at this video. If you have any questions or would like a copy, please let me know. And with that, I'll conclude.